Could you guess what we're going to do now? Yeah, and lesson 4 is called vector operations, and you can also call it vector arithmetic. I actually prefer vector arithmetic. Okay, so we're going to call this one scalar vector multiplication. So this is a definition of a vector arithmetic problem, multiplication. All right, so could you guess what we need to do scalar vector multiplication? Yeah, so let n be a natural number. Let a be a scalar. And could you guess what I'm about to write? I need a scalar and a vector. In this case, we might call it scalar column vector multiplication. Okay, so if it's column vector multiplication, it would have how many rows, how many columns? N rows and 1 column. And let's suppose that these are given. Then, scalar column vector multiplication is defined, and then I think I remembered this time not to go below the line, as the vector a times x. And the reason that we would, yeah, so I'll talk about that in a second. So let's see, this is a times, what does x look like? Yeah, these are called the coefficients of that vector all the way down to xn. Could you guess what scalar vector multiplication does? Yeah, so this is a x1, a x2, all the way down to a xn. This multiplication inside, what type of multiplication is that? That's called scalar mult. So it's mult in the real numbers. This thing right here, what type of multiplication is that? How would you know it's scalar vector? Write the dimensions. This is a 1 by 1. This is an n by 1. If it was matrix multiplication, what would have to be, or matrix vector multiplication, what would have to be true? The inner dimensions must agree. In fact, this is the only multiplication we're going to talk about in this class where the inner dimensions don't have to agree. In particular, this is a scalar, that's a vector. What's the multiplication called? Scalar column vector multiplication. Could you guess what scalar row vector multiplication is? Yeah, so maybe we say that y, what's the difference between a column vector and a row vector? Tell me what you mean about direction?
Direction they go in, like the way it expands.
The way that you write it. Yeah, you got to be a little careful, because usually when people use the word direction in the context of vectors, they're talking about how it points, and that's not what's happening here, right? It's not about how it points, it's about how we write it. How do we write column vectors? Partitioned by rows. So a column vector is a single column partitioned by rows. What's a row vector? A single row partitioned by columns. Okay, so let's go ahead and look at that thing. So we have what we call scalar column vector multiplication. We also have what we call scalar row vector multiplication. Could you guess what that looks like? A times y. Okay, let's go ahead and analyze the dimensions. What's a? 1 by 1. What's y? 1 by n. So let's go ahead and look at this thing. So this is a times, what does 1 by n look like? y1, y2, all the way down to yn. Okay, could you guess what scalar row vector multiplication does? It literally just brings it in, right? So y2 all the way down to a times yn. This thing right here, what's that multiplication? Scalar row vector. This thing right there, what's that multiplication? scalar multiplication. So each scalar vector multiplication represents n scalar multiplications. Do you see the compression of data? This is very, very famous of linear algebra. We write one multiplication, and we get a bunch of actual scalar multiplications underneath, right? So this is a very, very famous thing in linear algebra. A single scalar vector mult represents n scalar mults in R, which is quite powerful. That's one of the major reasons that linear algebra is so powerful.